So I'm going to show you some visualization tools we wrote. When I was a kid, I wrote video games just like a lot of us, and scientific computing's really benefited from this guy here, who is unfortunately died now. But he spent, I think, a decade of his life writing Matplotlib, which basically completely revolutionized scientific computing in Python. But there's something I don't like very much about Matplotlib, which is that it doesn't give you the real-time interaction that you need. So here's an example. This is heat plot. So let me just turn Pylab on here. So heat plot is something where you'd like to be able to see the data, and in Python here, first thing you need to do is turn off the default options. So the default options have this interpolation thing, and we want to turn that off. So we say interpolation equals none, and that's a good step forward, but that's still not exactly what we'd like. You still have to, highlight things with the mouse just to zoom in, and you can pan, but it's a little bit unwieldy, and you'll see why as we show some examples. So basically, we wrote some really lightweight visualization tools and put them in this Git repo here. So you can go get this yourself. It's at GitHub. So it's called Big Yellow Duck. But the main thing I wanted to show you is basically this heat plot thing here, and also a ggobi wrapper. We have also waveform viewing ability tool, and we have also a OpenGL version of MyGobi. Both of those are not yet in this repo. So this uses SDL, but we have a version, I think, that just uses Java. And we're going to hopefully have those soon. But here's one of our favorite data sets. This is probably something you recognize. But the point here is that you can quickly move through data. So you see these frame numbers being spit out over here. So that's nice. In fact, we could quickly move through all of the data. So here we're plotting all of the data, and if we change this frame number, which is the left and right greater than left than keys, actually allow us to move through all the frames, then we can quickly just visualize all of the data here. And you start to notice some things when you start to look at a lot of data very quickly, and here we see that for some reason near the end of the MNIST data it gets kind of crazy. And if you press the plus and minus key, you're quickly moving through different strengths of the heat. You can see there's some really funny things going on here. Like if we move over here, we press enter on a particular data point we want to see. Well, that one's 255, which is the maximum. We see the the row and the column index, and this is the index into all of the data if you want to just pick out that specific pixel, I guess. But you also see there's some pretty funny things going on in the data here, like that value is 255 there, but these values are 253 and 251. We can change the color maybe to get color scheme to see a little bit better what's going on for all these numbers, but there's definitely something kind of funny going on with these guys. And if you want to actually know what all these different keys are, we just like a keyboard because it's really fast and interactive like a video game. And here's a list of all the different keys. Alright, so maybe you want to look at just the training labels, and here is near the end of that the training data, and you see that you have these sequences here. So this guy starts at 0 and ends up at 9. So that's coming out there. But I basically showing you this because if you press the left and right square brackets, you actually change the width of this data. So you can quickly look at different widths, and you see that, well, there's something apparently going on at about 110 where these runs match up with each other for whatever reason. I don't know why there's these strange patterns in the MNIST data, but it lets me show you that you can change the width, which is nice. So here we're doing PCA on all the ones, and this is basically just to show you that we have a gGoby wrapper. I think there's such a thing in R, but if you try to find something for Python for scientific computing, you just find web pages where people say that would be nice to write. Well, we wrote it. The default behavior, I think, for this wrapper is if it has more than 1,000 data points, then it'll make them these tiny dots. If you do it with less than 1,000, it makes them big dots. Of course, you can change that. So here we see every single point is, these are the left singular vectors, so every single point is a particular sample, a digit, a particular drawing of one. So we can, of course, do the usual gGoby things, because it's just a gGoby wrapper. We have, like I said, an OpenGL version that we like to use that we don't have yet for you, but basically you can do usual gGoby things. So let's just mark some of these middle guys to see what they are. This is somewhat unwieldy, and I apologize, but it's just because I don't think gGoby gives us any better way to do it. If we copy that link, we have to save. If we want to pull it back to Python, we actually have to save this this file. So I'll just do that here. I think I just did. Okay. Okay, and so that pulls it back into Python. You see that it was given this name CL. So now we have that as an array in Python. This is just a bug, sorry. Okay, so if we have a look at this CL thing that we pulled back, we see that exactly 29 of them are the ones we marked. Let's just see what they are. Those middle guys that we marked, well, they're just the funny looking ones, which kind of makes sense that those might be in the middle, especially if you've think about it. Okay, so here's an example. We're looking at the right singular vectors, and now we're going to start messing with the color scheme and start looking at things a little bit more carefully. So this is the second right singular vector. The first one is just a DC component. The second one has sort of like the first mode, second mode. So SVD is recovering basically a Fourier thing. We can quickly step through those. We could also change the color scheme and sort of get a feel for what those right singular vectors look like. We could do a k-dimensional reconstruction of a particular data entry, and you see that the different right singular vectors are quickly approximating. And we see a lot of noise here, but if we turn down the contrast, we see that it's really, a linear model is doing a fairly good job at getting at the data. You see the frame numbers changing over here for reference, so if we just move through them quickly, you can see that happening. And one thing you could do, which is kind of nice, is you could go to a frame like this, frame 15, and if I press C a few times, I'll change the color mode, and this is actually a color mode where the R, G, and B channels are, for frame 15, 16, and 17, are giving you this plot. So you can see these colors are actually differences for different approximations. If we move all the way back to frame 0, it'll be pretty striking. So the DC component is green, and the red and blue are giving this this next guy. And we could move through several approximations and see those colors change. So that's nice. That's kind of useful sometimes. You could use the frames to go through and find, hey, where's the first funny one? Okay, well this is the first funny one at frame 5, and so then we could do the k-dimensional reconstruction for just that guy. Whoops. Okay, there it is. Just frame 5. Okay. Sorry. There. Okay. So we see that one gets approximated. Not that funny one is not quite as good, but you can still see a lot of the information. If we go back to do the multiple color mode, we can see it sort of slowly morphing into the thing we care about. Okay, so that's nice. We could do, and we can also do, custom things, but it's just really nice to be able to quickly move around with data. So here's an example where we've just plotted all of the samples using the actual data itself, and now we quickly move through the frames. We're basically doing what we did in gGoby, and you can see pretty quickly exactly what's going on. So these ones in the middle are the funny ones, so just like we thought, and this big arc is a phase term, a single parameter that's describing basically how tilted it is. So these guys are tilted like this, these guys are tilted like this, and we have a continuum all the way around. So that's what PCA tells us about the data, which is nice. So just to end here, I was going to compare the PCA stuff to what you might get with a neural network. Hey, forgive me, I'm using an autoencoder here just to see simply what dimension reduction might look like. Sorry, I know that you guys may not like autoencoders, but it's instructive to see what happens here. So first of all, here's the weights in the first layer compared to the weights in the second layer, and you can see that they're almost the same. The main difference is this is ReLU and this is, I think, the sigmoid. So you can really see the difference in that. Basically, all it is just shaping the data. So we could move through all of the weights really quickly. And basically, if you compare that to sort of what PCA is doing, this is what PCA does. PCA often recovers symmetries in data, so this is an example, and it's recovering basically the Fourier transform, essentially, because the data is continuous. This is the DC, and this is maybe the first mode, and so these are all just Fourier. So they look a little bit different than the weights. I picked up 32 of them. So you can quickly get a feel for what that looks like, and it does look different. But an interesting thing is if you do a Korkhoff, this is the top right mode, top right quadrant here is the actual relevant bit of comparing the 32 weights to the 32 singular vectors. And there's a nice color mode here, which is red and blue, and the red is like when it's positive, so that guy is 0.35, and the blue is negative, so minus 0.3. And I can turn up the heat. You can see that these guys, PCA has made them more or less independent, but there's still some noise. We turn it all the way down and all the way up, see what happens. It's pretty striking. If you do more than 32 from the SVD, you actually see that the data really does want to be about 30-dimensional, and that's just a fact about the data. I didn't say for it to do that. You can see it basically is dropping off in energy by the time we get down to right about there, which is 34, 32, so that's pretty cool. Alright, well, thanks for your time. Hopefully you can get used to visualizing things interactively like a video game instead of just relying on IPython Notebook, which is definitely a nice thing, but it's also really nice to be able to spin your data around very quickly from a command line. Alright, have fun.